Log on, tune in, find out. Another good idea from Cambridge.
By Cédric Bonnafé on his series on hacker algebras with unequal parameters.
Thank you very much. Well, so first I would like to thank the organizers for this invitation. And I would like to talk about ecoalgebras with unequal parameters. So you have certainly heard about ecoalgebras with unequal parameters in Meinhof's talk about switch. No. So how do we switch? It is. Okay. Well, so you have already heard about ecoalgebras with unequal parameters in Meinhof's talk about modular representations of these ecoalgebras and the way they are associated sometimes to endomorphism algebra of induced of cuspidal representations. So this talk, this series of lecture will try to explain the general algebraic setup for working with this kind of algebras. And I just want to start with some generalities which are really not related to ecoalgebra. So let's start with a commutative ring. And A, B, and R algebra, which is free. As an R module. So each time you have such a situation, you can define some pre-order relation on the set I as follows. You can define you can define first some relation like this. I is left related to J if there exists some A in A such that EI occurs, by this I mean that EI occurs in the decomposition of the multiplication of A by EJ. When you write this in this basis, it means that there is a non-zero coefficient on EI. So this is what I mean by this notation. Of course, you can define a right relation just by multiplying on the right. And you can define a left-right relation if there exists AB such that EI occurs in such a multiplication. Well, this you can do for any algebra which is free over the base ring. And of course, this relation is not in general transitive, but you can take the transitive closure. So the transitive closure is, this relation is a transitive closure of these partial relations. Well, this transitive closure is in general not an order, it is just a pre-order. And you can define the associated equivalence relation. Well, so X is equivalent to Y if X is less than Y and Y is less than X. Well, so once you have this definition, you can construct many ideals, left ideals, right ideals, or left-right ideals, according what you are working with. And for instance, so if C is a class, an equivalence class for the relation, for this relation, you can define A less than this class to be the free R module generated by all the elements EI, such that I is less than or equal to C. That you can, for the moment, this construction is elementary. But you see that, for instance, if in the case where you are working with the left multiplication, if you multiply by A on the left an element which is in this sub R module, then the result will stay in this sub module because of the definition. If you multiply AEI, you will only obtain elements which are less than or equal to the element EI. So you will stay in this guy. So this guy, this is a left, right, or two-sided ideal. Well, so this defines some ideal, left, right, or two-sided, and of course you can repeat this construction by taking the strict left preorder, and you can take the quotient. You can define V associated to C to be the quotient of A less than C by A strictly less than C. And then, well, and this guy is a left, right, or two-sided module or bimodule. Okay. And as an R module, this is isomorphic to the direct sum for elements in this equivalence class of R, and let's call EI tilde the image of EI in this guy. Okay? This is clear from the definition that you get some module easily by constructing these relations. Well, so let me give two examples. The first one is an easy one. You take A to be the group algebra of a group, G, which is free as an R module with bases indexed by the element of the group. And so you can try to see what is this relation. But the point is that in this case, the relation is trivial. Because you can obtain any element in the basis by multiplying this one by another element of the group, for instance. Okay? So this gives you really a trivial relation. So there is only one left, right, or two-sided equivalence class. And as a result, if you work out this construction of left, right, or two-sided module, you just get A as a left module or right module or two-sided or an AA bimodule. So this is not very, in some sense, this is not very interesting. There is no point in making such a construction to get just the free module of rank 1. Another example, a little bit more interesting, is the case of where A is the polynomial algebra in some indeterminate, which can be written, which is free with bases given by the different powers of t to the n. And in this case, it's easy to see that, well, here, left, right, or two-sided is not a problem because it is a commutative algebra. But you can get a power of t, the power tm, t to the m, by multiplying tn by something, only if you have, if and only if m, in this case, is less than or equal to n, is greater than or equal to n. So, in this case, the notation is not so good because this preorder is equal to this one. Okay. Well, and what do you get if you make this this construction? You get what is the module associated to some equivalence class. Here, the preorder becomes an order, and the equivalence class are just consist of only one element. And so v to the m is isomorphic to r of t over t. So this is the r of t module just given by making t act as 0. Okay? Well, so that's a little bit more interesting. You get some module. Well, we could have done a little bit better. So if an is a sequence in R, we define Pn to be the polynomial t minus a1 t minus an, just this product. So Pn plus 1 is a multiple of Pn, and so on. And in this case, this is still true. Well, first, A is also free with basis all the Pn. So this is still true because you can get Pn plus 1 by multiplying Pn by some element. And the module you get in this case, the module Vn is R of t modulo the ideal generated by t minus an. So if you choose your AI sufficiently different, you can get most of, almost, you can recover most of the simple modules for R of t, at least if R is a field. Okay? So this construction can, according to the choice of the basis, you see that you can get some uninteresting things, or sometimes you can recover most of the simple modules. Okay? Well, so that's what we are going to do in the case of ecoalgebras. So in the ecoalgebras, there is a standard basis, usually denoted by the TW. And if you make this this construction with the TW, you will get only, again, the free module of rank 1. So that's not the good basis to work with if you want to apply this kind of construction. So we will, the main point of Kazhdan-Lusztig theory is to construct a basis which will lead to interesting representations, not the free one, but representations of the ecoalgebra which are sufficiently small. And not only constructing representations which are sufficiently small, these representations are related with many geometric theory, for instance, the geometry of the unipotent classes, the geometry of the flag varieties, the theory of primitive ideals of enveloping algebras, and so on. And also, it is related to representations of finite groups of Lie type. So, I want to explain how this Kazhdan-Lusztig basis is constructed. So for this, I need to recall many notation about ecoalgebras and Coxeter groups. Well, so let's start with a Coxeter group. So I just recall that this means that W is generated by S, and that the elements of S are subject to relations like this. First, all elements have order 2, and if you take 2 elements in this generating set, then they satisfy a braid relation, where here the number of terms is an integer which is greater than or equal to 2. So this is the general definition of a Coxeter group. In the case this group is finite, it can be realized as a reflection, as a finite reflection subgroup over R. And if it is not finite, it can be also realized as a reflection group over R, but it's not included in Michel's talk. Well, for constructing the equal algebra, I also need gamma to be a group, abelian group. And I will denote by R the group algebra of gamma. And I will denote this group algebra with an exponential notation. So this is the sum for gamma in gamma of R exponential of gamma. And the multiplication is given by this formula. It's just because I want to use an additive notation for gamma. And inside the group algebra, I need to use an exponential notation. And the last ingredient to construct the equal algebra is a map that goes from S to gamma, and denoted by phi, satisfying that phi of S is equal to phi of T if S and T are conjugate in W. And once we have this setup, we can define the equal algebra H, which is H of W, S, and the map phi, which is the algebra, well, you have maybe be given many definitions of this, but I will give one. It's an algebra which is free over W, having a standard basis TW, and the multiplication is determined by the following condition. First, TW prime is TW prime, but of course not always, for otherwise it will be the group algebra. So if the length of W prime equals the length of W plus the length of W prime, here the length from W to N means the minimal number, the minimal length of a sequence of elements of S, such that the product is equal to the element. And the TS satisfies a quadratic relation, which is given like this. So phi of S. So you see that the map phi appears here as a parameter for the equal algebra. And so that's the reason for calling it unequal parameters, because we allow phi to take different values on the generators of W. So let me give one example that will follow us all along this series of lecture. I will talk about the case of the Weyl group Wn, which is a Weyl group of type Bn. Which has the following presentation, and I fix the notation T S1, S2, Sn minus 1, and I denote by b the value of phi at t, and by a the value of phi at S1 Sn minus 1, because all these elements, S1, S2, and Sn minus 1, are conjugate in the val group. So the map, the function phi, must take the same value on all these guys. And if we denote q to be the exponential of b, little q to be the exponential of a, so I recall that the a and b are elements of my group gamma, then this relation is not changed, but the quadratic relations becomes the following one. So this is equal to 0, and tsi minus q, tsi plus q minus 1 is equal to 0. And for those who are not used to this setup using the group algebra of gamma, I'm going to give two particular cases. And I hope they will convince you that making this assumption that is working with gamma is gives you a sufficiently flexible possibilities for dealing with many kind of algebras. So, for instance, if gamma is just, as an abelian group, is just z, what is z of gamma? Well, in fact, this is just the Laurent polynomial ring in some indeterminate, the indeterminate being the exponential of 1, if you want. Okay? And in this case, the relation here becomes tt minus v to the b, tt minus plus v to the minus b equals 0, and tsi minus v to the I a tsi plus v minus a equal to 0. So here you recognize your usual ecoalgebra when you have only one indeterminate and when the parameters are powers of this indeterminate. Okay? So you recover something that you might be used to. Another case that can be taken is to take gamma to be Z2. So the free abelian group of rank 2. Take B to be 1, 0, A to be 0, 1. That's a choice you can make for your parameter function phi. And what is in this case z of gamma? Recall that q is the exponential of 1, 0, little q is the exponential of 0, 1, but in fact this guy is just the Laurent polynomial ring in q and q inverse. And capital Q and little q are algebraically independent because B and A are linearly independent. That's equivalent. Okay? And you see that in this case, you recognize the generic ecoalgebra, the most generic ecoalgebra you can build. And you see that this allows, for instance, to specialize capital Q and little q to whatever you want. Okay? So that's a reason for not only working with this particular case, where you have only one indeterminate and parameters are power of this indeterminate, but it can be interesting to work with the general situation. Okay. So So as I have said, the point in Kazhdan-Lusztig one of the points in Kazhdan-Lusztig theory is to build a basis of the equal algebra, for which the construction, which is given here, gives you some interesting module of this kind. And for this, it's an easy exercise to check that if you work this construction with the standard basis, TW, you don't get anything interesting. So let's try to construct another basis, namely the Kazhdan-Lusztig basis. So for constructing this basis, we need two extra ingredients. The first one is an involution on the equal algebra that I will denote by bar, and it sends an element of the base ring here. This is the base ring is R is Z of gamma, and it sends it to the exponential of minus gamma. If you prefer, in this case, it means just that it sends V to V inverse, and it sends capital Q to capital Q inverse and little q to little q inverse. And it sends TW to TW inverse inverse. It's an easy exercise to see that this guy is invertible. You take this inverse, and because of the particular shape of the relations, you can check that this is an anti-automorphism, an automorphism of ring. It is not R linear because this automorphism acts on R, so it is R semi-linear because the bar is also acts also on R. And in fact, it is in involution. And the second ingredient we need for building the Kazhdan-Lusztig basis is an order on gamma. So gamma is a group, and I want to order its elements, but I don't want to order them arbitrarily. I want that this order is compatible with the group law. So this means that gamma becomes such that gamma is a totally ordered abelian group. Well, since gamma is a totally ordered abelian group, it implies in particular that gamma is torsion-free. So that's why I focused on the case of Z and Z2 here. I didn't take finite groups, for instance, for gamma. Well, okay. So we can denote R less than 0 to be the sum for gamma less than 0 of the R exponential of gamma. So this means all the monomials involving only negative elements in gamma. And H less than 0 is the sum for W in W of R less than 0 TW. So H less than 0 means all the elements in H which can be expressed in the standard basis only by using monomials of this form with elements which are negative. In some sense, in this case, well, let's go back to this case. What can be the order? What can be the order that can be chosen on gamma? So in this case, there is only one order. Well, there are two, but they are symmetric. You have to decide whether one is positive or negative. Well, let's be classical and choose that one is positive. And then you have an order on gamma. What are the order on Z2? So there are many orders on Z2. The first one is the lexicographic order. You have two elements, and well, the lexicographic order is compatible with the group law. And there are also many other orders that can be built by embedding, for instance, Z2 in R. You can embed Z2 in R, the field of real number. And this can be done by using an irrational number. You consider the map that goes from Z2 to R, that sends Mn to M theta plus N. So this gives you an injective map, and you decide to put on Z2 the order which is induced by this map. So this gives you an order less than or equal, that I will denote theta. It depends really heavily on theta. This is an order on Z2. And in fact, these are all the possible order you can put on Z2, all up to the automorphisms of Z2. You have many, many automorphisms of Z2. But if you change all these orders, you get all possibilities. Well, once we have fixed this order on gamma, once this is fixed, then there is a theorem by Kazhdan and Lusztig. It's not a difficult theorem. That tells you that you can construct some particular basis of H. So if W is in W, there exists a unique CW in H satisfying the following two properties. So first of all, CW is fixed under the involution, and CW is almost TW up two elements in this H less than 0. It means that the difference between CW and TW only involves monomials with negative powers. Yeah. Well, in fact, the proof of this theorem is pretty easy, and I will almost give it. So how can we prove this? First, let's deal with the uniqueness. So if you have two solutions to this problem, you can compute the difference, and the difference between these two solutions will satisfy two properties. So if C is equal to C bar and C is less than belongs to H less than 0, then C is equal to 0. And why? So write C to be the sum for W in W of AW TW. Then assume that C is different from 0, and take W be maximal for the length such that A of W is different from 0. It's not an element which involves only negative powers. And in this case, if you compute C bar, you obtain AW bar TW plus the sum for x different from W of AX bar TW inverse inverse TX inverse inverse. But what does it look like, this guy? AW, okay, no, non-zero, you're right. No, you're right. Well, so what does it look like? So write W is equal to S1 SR, reduced expression. And then TW is equal to TS1, TS2. Well, in fact, TW inverse is TSR, TSR minus 1, TS1. And TW inverse, W inverse inverse, is just TS1 inverse, TS2 inverse, TSR inverse. And the inverse of TS1 by the quadratic relation which is given here, this is just TS1 plus the exponential of phi of S1 minus the exponential of minus phi of S1. Am I right? I think so. Well, and if you compute this product, you see that you obtain TS1, TS2 up to TSR, so you get TW, plus what you will obtain only involves elements which are less than, for the Bruyère order, to W. So plus a sum for x less than W of RXW TX. I don't care about what they are equal to. But if I come back here, you see that this becomes equal to AW bar TW plus a sum involving elements x different from W and the length of, x different of W of something. Okay, you get here you get a part which comes from here, and then you get elements which are different from W. And on the other side, you have that this is also equal to C, which is equal to AW T of W plus the sum for x different W of something. Well, so this gives you that AW equals LW bar, but since C is an element of H less than 0, So AW only involves monomials with negative powers. So this equality can occur only if AW is equal to 0. Well, which contradicts the fact that AW is different from 0. Okay? So this means that no element except 0, no element in H less than 0 can be equal to its image by the bar involution. And this gives you the uniqueness in Kazhdan-Lusztig theorem. And what about the existence? I don't want to write exactly the proof of the existence, but just I hope to make you feel how it's possible to construct this CW. So first of all, and for this I will do it in the case of B2. TS, this is S1. On what?
The map from S to gamma.
I don't need, I think. What?
I mean, if P is trivial, it doesn't work.
What do you mean by trivial?
If it sends everything to 1.
Well, so you mean the 0 for okay? No, the existence will work because TS square, the bar involution only is the identity. This is the identity on TW. It's not the it's also the identity on. It's not the identity on R, but it's the identity on the TW, and TW will be the Kazhdan-Lusztig basis in this case. That's so. In the trivial case, this becomes an interesting example of the beginning. Well, so here we have two parameters, B, A. And, so according to your remark, I can assume that B and A are different from 0. And even I will assume that they are greater than 0. I want just to give the proof in this case, even though it's possible to give a proof in all the cases. So let's see what happens. So first, we can take for C1 to be T1, because it's stable under the bar involution, the neutral element. And it's congruent to T1 modulo whatever you want. What about CS? You can check that this guy I recall that capital Q is the exponential of B and little q is the exponential of A. So you can check that this guy is invariant under the bar involution, and it is congruent to TS modulo only something which involves negative powers. Okay. The same is for CT. And you can try to compute CS times CT. And you see immediately that this is TST plus Q inverse TS plus Q inverse TT plus Q inverse Q inverse. Well, the product of two elements which are invariant under the involution is also invariant under the involution. It is congruent to TST modulo a negative. Sorry? It's not an anti-evolution, it's an involution, I have said. It's really an involution, because there is two inverse. That makes it. Okay? So here, this guy is forced to be equal to the CST we are looking for. So let's go further. So let's compute CT times CST. Well, I don't want to write everything, but because I have only to work modulo the negative power, the negative part of H. So if I multiply the, CT by CST, I will get T and index TST. Well, CT, this is TT plus Q inverse, so Q inverse will give only negative power, so modulo H less than 0, I can forget about this guy, the multiplication by this guy. And if I multiply by TT, this guy, I get this. By TT, this one, I get something which is also in the negative part of H. If I multiply TT by this, I will also get something, but here, something can occur. So you get Q minus 1 times TT square, and that's all. Modulo the negative part, you get only this. But TT square, this is equal to 1 plus Q minus Q inverse TT. So finally we get that CS times CT times CST is equal to T is congruent to TTST plus, well, the 1 will multiply by Q inverse will live in the negative part. Little q inverse, capital Q inverse will also live in the negative part, and we get this. So I recall that this is the exponential of b minus e. Okay. And then you see what happens. You see that the Kazhdan-Lusztig basis will really depend on the parameters, or for instance in this case, parameter does not change, but the order on the group change. And you see that here you will have two different cases. So if B is less than A, this element lives in the negative part. So because of this, this congruence, you get that CT times CST is equal to CTSD. So you have constructed your CTST. If B is equal to A, this is allowed, then you get here a coefficient which is equal to 1. 1 is not in the negative part. But if you compute CT times CST minus CT, you subtract CT, you will get something which is congruent to TTST modulo H less than 0. And this tells you that this guy is the Kazhdan-Lusztig element you are looking for, because this guy is clearly invariant under the bar involution. And if B is greater than A, then, well, you must subtract something, but you must subtract something which is stable under the bar involution. And you get easily that CT times CST minus QQ inverse plus Q inverse Q CT is congruent to TTST modulo H less than 0. It's an easy computation. And this tells you that now this is our guy, CTST. Well, of course, this is only an example. And, well, it tells you how to construct the Kazhdan-Lusztig basis in general. You you assume that you have, by induction, you have constructed the Kazhdan-Lusztig basis for all elements up to a certain length, and you want to go a little bit further. You compute such an element, a CSCW, whenever SW is greater than W. You will get some TSW plus other things modulo the negative part, but you will try to subtract elements involving only the Kazhdan-Lusztig basis for elements of length strictly less, and by an easy induction process, you can prove that the result you will obtain is congruent to the right thing modulo the negative part, stable under the bar involution, and you will get your Kazhdan-Lusztig element. Okay, so that's the way that the proof can proceed. You can get the CSW, so you can obtain any Kazhdan-Lusztig element by this easy induction process. Well, it also shows that the Kazhdan-Lusztig basis depends heavily on the choice of parameters or on the choice of the order. Here, for instance, I have said that the parameters are always the same, but if you change the theta, for instance, the irrational number, meaning B is less than A in this case, B is less than A, this is equivalent to say that theta is less than 1. B is greater than A is equivalent to say that theta is greater than 1. So according to the entire part of the irrational number you have chosen, you have different Kazhdan-Lusztig bases. Okay? Well, so in the course of this induction process, here, you can get many properties of the Kazhdan-Lusztig basis. So let's write y to be the sum for x less than or equal to y, p x y star, well, x in w of tx. So let's express the Kazhdan-Lusztig basis in the standard basis. If sy is greater than y, write cs cy is equal to csy plus a sum for x in w of some coefficient that we call lambda x, y, s, for lambda for left, cx. So let's write formula like this, and you get following theorem. First of all, pxx star is equal to 1. The coefficient of t pyy of ty in cy is always equal to 1. You can check on the different formulas, at least on this example. You get that pxy star is different from 0, implies that x is less than or equal to y. The second another property is that if lambda x, y, s is different from 0, then sx is less than x is less than y is less than sy. So this is sy greater than 1, y is already given. But this forces, when you have a non-zero coefficient here, this forces this relation. And the last thing is that if SW is less than W, then CSCW is equal to exponential of I of S plus the exponential of minus phi of S times CW. So CW is an eigenvector for the left multiplication by CS. So I won't give the proof, but it follows by following very carefully this induction process. Well, and this guy, in the equal parameter case, usual, are up to a power of v are the well-known Kazhdan-Lusztig polynomials. Well, let's see an example. Well, so now, well, before an example, we can define the pre-order by using the Kazhdan-Lusztig basis. So just an example, x is less than y if there exists h in h such that cx appears with a non-zero coefficient in the multiplication on the left of cy by h. And we can do the same thing as we have done at the beginning. And so this gives you equivalence relation, and the equivalence class are called the left, the right, or the two-sided cells. Well, so let's see what happens in the case of B2. Well, so you have W0, which is ST. You have TST, ST, T1, STS, STS. Well, so if you multiply C1 by CT, you get this guy. So here you have a left relation. I omit the L, but I just talk about left multiplication, the left cells, the left pre-order, and so on. Here, if you multiply by CS, you get CST. If you multiply by CT, you see that it depends. If B is less than A, you get CTST. If B is equal to A, you obtain some other thing, but you always get CTST. And sometimes you obtain CT CT occurs with a non-zero coefficient in the multiplication of CT by CST. Okay. So here, this is the case where B is less than A. Here, this is the case where B is equal to A. And the last one. Well, so this relation you always have. But sometimes you have also, in the case where B is equal to A, you have this relation, and you also have it here. Okay. So you see that the picture is different according to the value of B, and the different values of B and A. This is the last case. And if you go on, Well, in this case, if you multiply this guy by CS, you get this guy, but you also get this one. If you do it in this case, it also works. And if you do it in this case, you multiply this guy by CS, you get only CW0, you don't get anything else. And on the other side, you get something that looks like this. Yes, that's it. Okay. And it tells you that according to the choice of the parameters, the left cells, which are the equivalence class, so this guy is less than this one, and this one is less than this one, so this is a left cell, this is a left cell, here this guy is alone, is in left cell, and so on. Here you have a left cell with 3 elements, 2 left cells with 1 element, and here you get these different partitions into left cells. Well, okay, so I will come back tomorrow to this example to explain what interesting things can be seen from this example. For instance, you see that you obtain modules of dimension 2, 2, 1, 1, and 1, and 1. So you get all the irreducible modules for B2, for the ecoalgebra of type B2. But not only you get irreducible modules, you get also an R form of this module. You get a form over this ring of integers. So that gives you different forms of the irreducible modules. And in this case and in this case, you don't get, they are not isomorphic. If you extend to the field of fractions, you obtain isomorphic module, but at the level of this ring, they are not isomorphic. So it gives you different integral models for the irreducible representations. So I think I will stop here.
Thank you. Are there questions, remarks? Okay, so we have a coffee break until 11:30.